Hi everyone, this is Lewis Structures, and we're going to be looking at the rules for drawing covalent compounds. And these, of course, are the same as our molecular solids. So to start off with, let's look at Sedgwick's contribution, and that is that one atom could contribute both electrons in an electron pair instead of just one from each atom. This is called a coordinate bond, and we're going to see some of this happening with our molecules. The second thing that we're going to see is that most atoms want an octet, which is 8, but not all molecules will want an octet. We're going to see that we typically want an octet or more. So again, octet means 8 electrons in its valence shell. But again, we can have an octet or more, and we have one exception. We can call this the weirdo of the Lewis structure world, and that is boron. Boron actually prefers less than an octet, as we will see. We have 6 rules when we're drawing our Lewis structures. So our first rule is to count the number of valence electrons on our compound. Remember that when we're looking for valence electrons, we can use the column number on our periodic table. If we have negative ions, negative means electrons have been gained. So anytime we have a negative ion, we're going to add electrons to our count. And anytime we have a positive ion, we're going to subtract electrons from our count. This count is really important because it's going to set us off on the right track for success. And this count should always be an even number. Think about when we put electrons into orbitals in quantum. Every orbital holds 2 electrons before it is filled. So electrons will travel as pairs and they will fill orbitals as pairs. In step 2, we're going to put the unique atom in the middle. The unique atom just means the one that you only have one of, typically. It goes into the middle. The other atoms will be placed symmetrically around the outside. In number 3, we're going to start using those electron pairs from our first count in step 1. And the first pairs are always put between the central atom, which is the unique atom, and the surrounding atoms. Next, we're going to put the electron pairs around the surrounding atoms to make sure they have an octet. An exception to this will be our hydrogen. Remember, hydrogen only has a 1s orbital and it maxes out at 2 electrons. But all the other atoms that are surrounding atoms will want an octet. Again, octet is 8. In step number 5, we're going to count how many electrons are in our picture at this point, and then we have 5 choices from this point forward. Part A, or type A, I guess we would call it, is if the central atom has an octet and you've used up all available electrons from the count in step 1, you have completed your picture and you can go to step 6 and make your good copy. That's the easiest scenario. Type B is if the central atom has an octet, but there are leftover electrons. And in fact, you don't actually have to have an octet here. This is actually, I'm just going to put this as a question mark for octet because it could have an octet or it might not have an octet. But the key for a type B is you have leftover electrons. Leftovers means your original count in step 1 has a higher number of electrons than your picture. So let's say your picture has 40 electrons, but in step 1 you counted that you should have 42 electrons. That means you have extra electrons or leftover electrons in your count. Those leftovers have to become part of your picture. You're going to put them always on your central atom. That's always where those leftovers can go. This could give you an octet. So for instance, if you did not have an octet, this might give you an octet or it might not. If you add those extra electrons onto your central atom and you still don't have an octet and you're out of electrons, then you're going to go to stage 3 or stage C. And this is if you have a central atom, you don't have an octet, so no octet, does not have an octet, and there are no more leftover electrons, so you may have none in the beginning, but you may have had some but not enough, so lots of options here. You're going to create that coordinate bond, which means you're going to share electrons more than once between 2 atoms to create a multiple bond. And you can share twice, meaning a double bond, or you can share 3 times, making a triple bond between 2 atoms. So this is our exception to that rule. Remember, boron is a little guy. He's this very small atom on the periodic table. So everything but boron wants an octet or more in terms of electrons if you're the central atom, but boron prefers to have only 3 bonds which is the equivalent of 6 electrons around it. So boron will be our weirdo for the Lewis world. Our step 6 is just making a good copy. So basically we're going to redraw our structure, and the thing that will change is we're going to represent our bonding electron pairs as lines. So that's the thing that will change. Everything else pretty much stays the same. And if you have an ion, you're going to put a square bracket and charge around that ion in the upper right hand corner to finish that off. So let's see this all in practice. Example number 1, we have OF6. So using our periodic table, we want to look at the column number for each of our elements to determine valence electrons. So oxygen is in column number 6. It has 6 valence electrons. We've got 6 fluorines. Fluorine is in the 7th column, so it has 7 valence electrons each. And then we're going to add them together for a total of 48 electrons. So I now need 48 electrons in my picture. The next step, stage 2, is to put the unique element in the middle, and oxygen is the unique one, meaning one of. And then step 3, or part of step 2 rather, is you're going to put the surrounding atoms just symmetrically around the outside. Now it's time to put electron pairs in. So in step 3 it tells you the first pairs of electrons are always going between the central atom and the surrounding atom. These are my bonding electron pairs. A hard time making dots there. And so those are the first pairs that always go in because they're my bonding pairs. They're the most important. Now my surrounding atoms will get their octet of electrons. Oh, here we go. Come on, pen. What is going on? It only wants to make one dot at a time. You know what? I'm going to pause and I'm going to put all the dots in for you. As soon as I paused the video, all the dots were working just fine. Oh, technology. Bane of my existence. All right, at this point we're at stage 5. And stage 5 means count the electrons in the picture. I would count by groups of 8 because you can sort of circle up a group of 8 here, for instance. Oh, of course that one's missing an electron. Seriously? Seriously, this is my life right now. I had to pause it to create that dot. What on earth is happening? I'm being sabotaged. So you can count by groups of 8 here, and we have 6 groups of 8, so that would be the quickest way to count. If you're not very good at your 8 times tables, that's cool too. I'm not going to judge. But you could count by 2s, for instance. That would speed things up just a little bit. Let's get rid of, whoopsies. Let's get rid of that. Oh. And so we have 48 electrons in our picture. So that means we get to go to step 6, which is our good copy. So because I have a tool to erase, and you might have drawn in pencil, which means you can also erase, you might want to just get rid of these electrons in the center, and then you're going to replace them with a line. And that just means it's still an electron pair, but it's a special type. It's a bonding type. So it's just a way of saying this pair is a bonding pair of electrons as opposed to the electrons around the outside, which remain as dots, and we consider those to be called lone electron pairs. So that's our first example. Great job. Example number 2, we've got our NH3, same deal as before. We're using our column number to determine valence electrons. We've got 5 for nitrogen. We've got 3 hydrogens, and hydrogens have 1 valence electron each for a grand total of 8 electrons. Just like before, my unique element goes in the middle, and the others go symmetrically around the outside. Now it's time for electron pairs. Let's hope it works. And we're putting in those bonding pairs first. Well, see, it's listening to me. Now all of a sudden it's not. Oh, there it goes. Okay. So there's my electron pairs. And remember that a hydrogen does not need an octet. It's only got a 1s orbital that only holds 2 electrons total, and it's already got its 2 electrons. So now I'm on to step 5 already. That was quick. And I'm just doing my electron count and comparing. So in my picture I have 6 electrons, but I'm supposed to have 8 electrons in this picture. So this is a leftover situation. Leftovers always go on the central atom, so I'm just going to stick them at the top because there's lots of space there. And now I'm going to do another check, and that is an octet. I always have to make sure I have an octet or more. And in fact, on the nitrogen, I do have an octet, so that part is met as well, which means I get to go to step 6 and make my good copy. Again, because I have an erasing tool, I'm just going to erase my, erase part of that in. I'm going to erase my bonding pairs and replace them by lines. And there is my second example. Boop, boop. All right, example number 3, NO3 with a 1- charge. Let's knock this one out. So my nitrogen is in the 5th column, 5 valence electrons. I've got 3 oxygens in the 6th column. And I've got this pesky 1-, which means add an extra electron for a grand total of 24 electrons here. Again, nitrogen is my unique atom. It's going in the middle. And then I'm going to put my O's symmetrically around the outside. Time to put electrons in. I'll pause it for you. You can thank me later. So those are my bonding pairs. Now I'm going to put octets in for each oxygen. There we go. And now I'm going to count the electrons in the picture and compare it to the total. So in my picture, I have 24 electrons. I'm supposed to have 24 electrons, so that part's good. And then the second thing I need to check is, does my central atom have an octet? This is a no. There are only 6 electrons around nitrogen, and it wants 8. Well, here's the problem. I've run out of electrons. I only had 24 to use, and I used them all up. So here's where I'm going to make that coordinate bond. All I have to do is take a pair that's not really doing anything, and I just have to shift them over so they can share more than once. So I'm going to redraw this one for you so you can see it a little better. So on the left-hand oxygen, because I'm sharing twice, I now have created a double bond, and the other 2 are still going to remain as single bonds. Remember that every stick I've drawn is an electron pair, so I've got 4 sticks times 2 electrons. That's 8 electrons around the nitrogen now. So that's how I'm going to give it an octet. As usual, I'll have those electrons around the outside, those in for you. And then the last thing I want to do, because it's an ion, I have to take that extra step and put the square brackets in the charge in as well. There's one more type of picture we're going to practice, and that is oxyacids. So oxyacids are hydrogen bonded to a polyatomic ion. And when it comes to oxyacids, the hydrogens are going to bond to the oxygen, not the central atom. And that's the key to drawing oxyacids. We'll do an example of that in a moment, but just a note for homework, when you see any molecules tonight for homework that start with an H, you're going to assume that those are your acids. When I give it to you on a quiz or a test, I'll be more explicit, and I'll do something, for instance, like H2CO3, and I will also include AQ, because we know that acids always have to be aqueous. So that hydrogen in the front and that aqueous at the end will make it just a little more certain that we're dealing with an acid. However, your textbook, anything that starts with an H is going to be an acid. So let's do an example of H2SO4. And you're going to find it starts the same way as the other questions. So again, just coming up with my electron count here, the same way I always do. And we've got 32 electrons for this picture. Oops. And again, I'm just going to put the unique element in the middle. So in this case, my sulfur. I'm going to put my oxygen symmetrically around the outside. And here's what's new. I'm going to put the H's next to the O's. So I'm going to put one H next to each of the O's here. And the O's will only bond to 2 things in total. So I don't want 2 H's on one O. However, which 2 O's I choose could be any. That doesn't make a difference. All right, let's put in our bonding pairs of electrons. Of course, I'm going to have to pause, a little like magic there. And then I also want to put bonding pairs in between the O's and H's. Oh, I got it this time. And then those are also going to be bonding pairs. So now I can do this surrounding atoms. So my oxygens will now get octets. There we go. And now I want to count. So I have 32 electrons in the picture. So that part's good. And now I want to check for an octet on the surrounding of the central atom. Sulfur does have 8, so it has an octet. So I am now ready to go to my good copy. Once again, I have the privilege of just erasing. And don't forget, of course that did that. Don't forget the bonds that you have between the oxygen and the hydrogen. So I'm going to put those in. A little sloppy looking, sorry about that. But all of the bonds, remember, get replaced with that line to indicate that they are bonding pairs. And there is your homework. Yay, it's practice time.